Alright guys, sorry, yeah. I wanted to solve this myself to show you the stepwise process. Okay, so let's do the circuit again. This was an step response of an RC circuit. Here's an example problem, kind of interesting. And what this example problem entail is that at time t equals to 0, the switch moved from position 1 to position 2. So this means that at time t is less than 0, it was at position 1, and then at time t equals to 0 or greater than 0, it will be at position 2. So we would consider the right part of the circuit. Okay, so let's solve for these things. So part number A, in part number A, we have to find the capacitor voltage for t is greater or equals to 0. Okay, and we just saw how to find that out, right? We derived an entire equation, and we saw that in order to solve for that equation, we need to find the initial voltage of the capacitor, final voltage of the capacitor, and the time constant. Now let's start with determining the initial voltage of a capacitor, right? So initial capacitor voltage, which practically means that before the switching event, what was the capacitor voltage? If I draw the circuit at t is less than 0, circuit at t is less than 0, essentially it's the left hand side of the circuit. I would get 40 volts, this, right? So this is 40 volts, 20 kilo ohms resistor. We have a 60 kilo ohms resistor over here as well, and then we have a capacitor. We don't know how much time was passed, but we are going to assume that sufficient time was passed, the capacitor was fully charged, right? If we draw a circuit as less than time 0, we have an excitation source there. So this means that capacitor was charged to some level. And there was no capacitor was fully charged, because we're going to assume that a long time has passed or sufficient time was passed, the capacitor was fully charged, right? If the capacitor was fully charged, so this means that our assumption is it is fully charged. We are going to realize that capacitor will become an open circuit, as we have discussed this innumerable number of times now, right? So this is going to be by V naught, since it will become open circuit, right? Okay, so at t is less than 0, say assume capacitor is fully charged because of a 40 volt source. Okay, in this case I can easily see that my V naught over here, it can simply be found by doing a voltage divider rule across a 60 kilo ohms resistor, right? So I can apply a voltage divider rule, and I know that V naught should be equals to the voltage, source voltage, 40 volts, times the resistance across which we are measuring the voltage, 60k, divided by the summation of the resistances, 60k plus 20k. So if I were to solve this, I would get initial voltage of the capacitor to be 30 volts. Okay, so this is good. This is the initial voltage of the capacitor. So I ended up finding the first thing. The second thing I need to find is the value of the time constant. Time constant tau needs to be found, and we know that we usually find this by solving the circuit at t is greater or equals to 0. So let me redraw the circuit again. At t is greater or equals to 0, right? So now I'm going to have a capacitor, and I'm going to have a resistor as well, another resistor, and another source. So this is 475 volts, 40k, 160k, 8k, and then what do we have over here? We have 0.25 microfarads. Okay, and I know that tau equals RC. I know the value of the C, I know the value of the R, so I can easily find the value of the equivalent resistance. If I look at the circuit, I can easily see that my 40K and 160K are in parallel to each other. So 40K in parallels to 160K, and that is in series with 8K. So if you like, you can solve this, divided by 200 plus 8. Once you're going to solve this, you're going to find out the total value of the equivalent resistance is going to come out to be 40 kilo ohms. So I can replace both of these values. Tau equals 40K times 0.25 times microfarad, 10 to the power minus 6, and this is going to come out to be 10 millisecond. Okay, so this is the value of the tau here. Okay, so we ended up finding all the, no, the third thing is still, we need to figure it out. What is the final voltage value? Okay, before we write down the equation. So third thing is we need to find the final voltage value. And again, this is found when at time t equals to infinite. Again, at time t equals to infinite, your switching event at least have happened, right? Because that happened at time t equals to 0. So we are essentially talking about this circuit. But we are talking about this circuit at time t equals to infinite. Very, 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 very long time. This means that my capacitor should become open circuit again because a new steady state has been reached. Okay, so I'm going to redraw the circuit now. So I will get, 8K, 160, 40K. So this is 75 volts, and then you have 40, 160, 80, 40K, 160K, and 8K. And this is a capacitor final voltage value. Again, this is when time approaches infinity because a new steady state has been reached. Of course, this is going to reach way before infinity, by the way, because we know that after 5 time constant, things are pretty much at the steady state. Okay, I can easily get this value, and again, this is another voltage divider rule. I don't care about the 8K over here because VF is open circuit. So VF across 160K should be equals to minus 75. Consider the polarity of the source here, times 160K divided by 160K plus 40K. If you were to solve this, the answer is going to come out to be minus 60 volts. So this is the value of the final voltage that you have. So we ended up finding all the three things. We ended up finding the initial voltage, the final voltage, and the time constant. So now all we need to do is to replace everything in the capacitor voltage equation that we derived, which is equals to the final voltage value plus initial voltage value minus final voltage value e raised to power minus t over RC. So V of t should come out to be minus 60 plus V naught is, what was V naught? 30 volts. 30 volts minus 60 should come out to be plus 60 e raised to power minus t over RC, and RC is again your time constant tau, which was which was how much, 10 millisecond or 0.01 second. So I'm going to do 0.01, right? So this is minus 60 plus 90 e raised to power, and again 1 divided by 0.01 comes out to be 100 minus 100 t volts, and again 4t is greater or equals to 0 and V of t. So here's the equation for the V of t that we ended up deriving, right? Yeah, so this is V naught of t. Yeah, of course you can use V naught of t. Yeah, V naught of t. But essentially this is a capacitor voltage. Let's find the value of the current, right? And again, this is a capacitor current as well. It is flowing over here. And interestingly, I have made this point like so many times. Let me make it one more time, right? As you can see, the capacitor voltage is greater or equals to 0. The capacitor current is greater or equals to 0 positive. The reason for that is, I'm going to ask this conceptual question in the exams. The reason for that is capacitor, I wish I would have been asking this in person. The reason for that is the capacitor voltage does not change instantaneously. So it is going to behave as an open circuit. No current is going to flow. So I naught only makes sense. The capacitor current only makes sense at time t 0 positive, and not before that, because it was an open circuit at that time, practically speaking. Okay, so let's solve for B now. And for B, it asks you to find the value of I naught of t for t is greater or equals to 0 positive. I already derived this equation, right? So C times dv naught over dt. And all you need to do is to take a derivative of this equation. So I naught of t equals capacitance, which is 0.25 microfarad, 0.25 microfarad times the derivative of V naught. Minus 60 is going to come out to be 0. And then you're going to left with 90 times minus 100 e raised to power minus t over RC. Or sorry, e raised to power minus 100t. I should minus 100t. Of course, you're going to replace RC by 0.01 seconds. Right, so if you were to solve this, I naught of t is going to come out to be 0.25 10 to the minus 6 times minus 9,000 e raised to power minus 100t. I naught of t minus 2.25 e raised to power minus 100t milliamperes for t is greater or equals to 0 positive. So this is the value of the capacitor current that is going to flow in the circuit. Okay, so this is the end of this example problem. Sorry, I have to upload this kind of a separate thing because I wanted to show you the whole stepwise process rather than the other thing. All right, with that, thank you so much. Have a great rest of the day. Thanks, bye.